All right, this one's just a bit more bizarre, and I hope I've interpreted what you're looking for correctly. The problem seemed to suggest that this was true, and then it wanted you to show that this simplified down to this for x between 0 and L. So let me go through some hard-hitting case 1, case 2 type stuff. And then let's revisit it from just kind of a visual way of understanding. First of all, case 1, and let me jump to the assumption, is there anything, it's kind of where I needed some more information, is there anything in the original problem that seemed to suggest that h needed to be greater than or equal to 0, positive? If there isn't, then I'm not quite sure which direction to take on this. Let me know and I'll have to rethink and revisit this whole thing. But this is based on an assumption that h is positive. If that's true, then let's take a look at this for x between 0 and L, with the case number 1 being, let's let x equal 0. Case 2, let's let x equal L. And those will be the extremes of this case. Well, if x equals 0, it's pretty clear that this portion just drops away. And you're left with 6h times v squared over L squared. You're left being greater or less than or equal to k. You're left with the exact thing that you're hoping it would be. So that's pretty basic right there. You know that this is going to be true. Now case 2, what about if x equals L? Well, if x equals L, if I put an L right here, and L right here is going to cancel with one of these L's down here, you'll have an L squared on the bottom. Now these are like terms with a negative 12 fraction plus 6 fraction that gives you negative 6, or just the opposite of that. So negative 6h v squared L squared is less than or equal to k. So the question then becomes, well, first of all, let's go to the assumption. If h is positive, then 6 is positive, v squared is positive, L squared is positive. This is a positive amount, and putting a negative in front of it is going to make it a negative amount, right? So if this right here is true, then this is also going to be true, because if a positive number is less than or equal to k, then its opposite is also going to be less than or equal to k. If 8 is less than or equal to 10, then negative 8 is also going to be less than or equal to 10. Good? And that takes us then to our visual idea of what's going on. For an inequality, we're not looking for an equation for this to equal this. In this case, we're looking for a condition. What's the simplest way we can state this condition? In other words, what is the maximum that this expression right here could ever be? And what we find is, starting with 0, 0 lets this thing be the maximum amount it can be. And for any number bigger than 0 all the way up to L, this negative component becomes more and more of a factor. This is positive. Introduce a negative number to it, and this positive value gets smaller and smaller and smaller. So what is the biggest this whole expression can be? The biggest it's going to be is when this negative component isn't there. And that's when this is 0. So let's drop it out. Since 0 is allowed in our original conditions, if x is allowed to be 0, then we can get rid of this, which means the maximum this amount will ever be is just this. So we can simplify this by saying, hey, you know what? The largest this is ever going to be, and we're concerned about it always being less than k. We don't care if this is negative a billion. We want to know what its maximum is. And as long as its maximum is less than or equal to k, then we're good. What is the maximum of this under these conditions? The maximum is when x equals 0, allowing this to drop out, giving us this right there. So that's what allows us to simplify this down to simply that. I don't know if that explains or if that's the useful thing about where this is going. Seems to be a pretty elaborate situation, but I don't know, chew around with that, see if that makes any sense to you, and send me an email back.